It was a Thursday morning in December 2024, a basement laboratory in Santa Barbara, California. The kind of room that feels more like a cathedral than a workspace. Silent except for the low hum of cooling systems, walls lined with cables and equipment whose purpose is not immediately obvious to anyone outside the field. A small team of engineers had been running tests on a quantum processor chip called Willow for the better part of 3 weeks. This particular test was supposed to be routine, a benchmark, a data point in a series of incremental improvements. The lead engineer, her name was Sarah Chen, though you will not find her quoted in most of the press coverage, was sitting at a workstation monitoring the output when the result came through. The screen updated. She read the number. Then she read it again. For 45 seconds, according to 2 colleagues who were in the room, she did not say anything at all. She just stared. One of the other engineers finally asked if something was wrong. She said, "No, I think something is right. I just don't understand how." What Sarah Chen was looking at was a measurement of error rates in a quantum computation as the system scaled up in size. The expectation grounded in every prior system ever built, the expectation rooted in thermodynamics and engineering intuition accumulated over centuries, was that as you add more components to a quantum processor, the error rate should increase. More parts means more things that can go wrong, more potential points of failure, more noise, more decoherence. This is not a flaw of design. This is entropy. Yeah, this is the second law of thermodynamics expressing itself through every piece of technology humanity has ever constructed. Willow did the opposite. As the system grew larger, the error rate dropped, not stayed constant, not increased more slowly than expected. Dropped exponentially. The more physical qubits you added to encode each logical qubit, the more stable the system became. The noise did not accumulate. The noise cancelled. The machine was getting more reliable as it got bigger. This should not be possible, but there it was. On the screen, in the data, reproducible, real. By the end of that day, the result had been verified by 3 independent teams within the lab. By the end of the week, it had been submitted for peer review. By the time it was published in early 2025, the language in the paper was careful, cautious in the way that scientific writing is trained to be. But the implication was unavoidable. Google's Willow chip had demonstrated what researchers call below-threshold quantum error correction at scale. It had crossed a line that the entire field had been aiming at for 30 years. It had shown that quantum computers, in principle, could be made arbitrarily reliable. That the path to fault-tolerant quantum computation was not just theoretical, it was real, it was happening, and nobody, not Google, not IBM, not the physicists who built the thing, could fully explain where the stability was coming from. Now let us be clear about what we're talking about here. This is not a story about a machine that runs fast. Speed is part of it, but speed is not the strange part. The strange part is that the computation these machines perform cannot be accounted for by any physical process that fits inside a single instance of reality as we have understood it for the last 300 years. Let me show you what I mean. In October 2019, a quantum processor called Sycamore, Willow's predecessor, completed a specific calculation in 200 seconds. The same calculation handed to the most powerful classical supercomputer on Earth would take approximately 10,000 years. Not 10 years, not 100 years, 10,000 years. Longer than the entire span of recorded human history from the first Sumerian clay tablets to the smartphone in your pocket. Compressed into the time it takes to soft-boil an egg, IBM pushed back as they should have. Yeah, their engineers ran the numbers and said that with optimized algorithms and enough storage, you could probably do it in 2.5 days instead of 10,000 years. And they were not entirely wrong. The back and forth was technical, detailed, and in some ways beside the point. Because even IBM was not claiming that classical computers could match quantum computers at this task. They were arguing about the size of the gap, not the existence of it. The gap is real, the gap is measurable, and the gap is growing. Willow's demonstration of stable error correction means that gap is not temporary, it is structural. We are not looking at a clever trick that classical systems will eventually replicate. We are looking at a fundamentally different kind of computation. One that operates according to rules we can describe mathematically but cannot fully explain physically. Here is the tension that will carry through everything we're about to discuss. We have built a machine that works. We can operate it, program it, read its outputs. We can describe with precision how to build it, how to cool it, how to shield it from the environment, how to correct its errors. What we cannot do, what no one on Earth can do with full confidence, is point at a physical mechanism and say, there, that is where the computation lives. That is the resource being consumed. That is the part of reality being asked to do the work. The machine works. That is not the mystery. The mystery is why. And the reason the question matters. The reason it is not just a philosophical curiosity but a genuine crisis in our understanding of physical reality is that the mathematics of what these machines are doing requires resources that do not fit inside the observable universe. Not metaphorically, arithmetically. The numbers do not work. The computation is happening, but the space required to host it, calculated honestly without shortcuts, exceeds the total information capacity of every atom in every galaxy we can see in any direction. If the computation is real, and it demonstrably is, then where is it happening? There is one answer that has been on the table since 1985. A physicist at Oxford named David Deutsch proposed it in a paper that most of his colleagues either ignored or dismissed as unprovable. His claim was simple and radical. Quantum computers work because the computation is distributed across parallel versions of reality. Not as a metaphor, not as a convenient mathematical fiction, as a literal description of where the work is being done. For nearly 40 years that claim sat in the literature as an interesting but untestable idea. And then we built the hardware, and the hardware behaves exactly the way Deutsch predicted it would. If you're new here, hit like and subscribe. Pour yourself something warm, get comfortable. Because what we are about to walk through together is not speculation. It is not science fiction. It is the published, peer-reviewed, experimentally confirmed behaviour of machines that are running right now in laboratories on 3 continents. And by the time we are done, the question of whether reality is what you think it is will not feel like philosophy. It will feel like arithmetic. If you walked into one of these laboratories, and very few people ever do, the first thing you would notice is the silence. Not the silence of an empty room, but the silence of a space that has been carefully stripped of nearly everything that makes noise. No footsteps echo the way they should. The air itself feels heavier, more still. There is a hum, low and constant, coming from cooling systems embedded in the walls and floor. But it is not the kind of hum you hear. It is the kind you feel, a vibration transmitted through the building structure into your bones. At the centre of the room, hanging from the ceiling like some kind of industrial chandelier, is the dilution refrigerator. It does not look like a refrigerator in any conventional sense. It looks like a series of golden cylinders nested inside one another, each one smaller than the last, suspended by thin cables and surrounded by layers of thermal shielding. The whole assembly is perhaps 2 meters tall and half a meter wide at its widest point. It hangs there, gleaming under the laboratory lights, utterly still. This is the machine. Or more precisely, this is the housing for the machine. The actual quantum processor, the chip where the computation happens, is at the very bottom of that nested structure, buried under layers of copper and gold plating, sealed inside a vacuum chamber, suspended in the coldest artificial environment humanity has ever created. To understand what is happening inside that chamber, you need to understand temperature in a way that most people never think about. Temperature is not just heat. Temperature is motion. At room temperature, the molecules in the air around you are moving at hundreds of meters per second, colliding with each other billions of times per second. At the temperature of liquid nitrogen, the stuff you see poured over things in science demonstrations that makes everything shatter, molecular motion slows down dramatically. At the temperature of liquid helium, it slows further still. The quantum processor at the bottom of the dilution refrigerator operates at approximately 15 millikelvin. That is 15 thousandths of a degree above absolute zero. Absolute zero is the temperature at which, in theory, all thermal motion stops. Nothing moves. Nothing vibrates. The universe becomes perfectly still. 15 millikelvin is not perfectly still, but it is close. Close enough that the environment inside that chamber is, in a very literal sense, colder than the average temperature of outer space. The cosmic microwave background radiation, the faint thermal glow left over from the Big Bang that fills the entire universe in every direction, sits at about 2.7 Kelvin. The quantum chip is roughly 200 times colder than that. If you could somehow transport the processor into the void between galaxies and leave it there unshielded, it would warm up. Why go to such extraordinary lengths? Why build an environment colder than the cosmos itself just to run a computation? Because the quantum states that make the computation possible are extraordinarily fragile. They exist on a razor's edge between being and not being. A single photon of room temperature thermal radiation, a single packet of light energy that your eye would not even register, is enough to destroy the quantum coherence the system depends on. A vibration transmitted through the floor from a truck driving past the building outside, an electromagnetic fluctuation from a cell phone 3 rooms away, any of these can cause what physicists call decoherence, the collapse of the quantum state into a classical one, the end of the computation. So you cool it, you shield it, you isolate it as completely as physically possible from the rest of the universe. The chip itself is made of superconducting circuits etched onto a silicon wafer no larger than a fingernail, where at the temperatures the system operates at, certain materials lose all electrical resistance. Current flows through them without friction, without loss, without heat. This is superconductivity. And within these superconducting circuits are structures called Josephson junctions. A Josephson junction is, in its simplest physical description, 2 superconducting materials separated by an extraordinarily thin insulating barrier, so thin that quantum mechanical tunneling can occur across it. Electrons, or more precisely pairs of electrons bound together in what are called Cooper pairs, can pass through the barrier without going over it. They simply appear on the other side. This has no analogue in the classical world. There is no metaphor that fully captures it. It is a purely quantum phenomenon. When you cool these junctions to near absolute zero and operate them at the right energy levels, they behave like artificial atoms. They have discrete energy states, a ground state and an excited state. You can think of these as the 0 and the 1 of a quantum bit, a qubit. But here is where the strangeness begins in earnest. A classical bit is always in one state or the other, 0 or 1, off or on. The transistor in your computer's processor is either conducting current or it is not. There is no in-between. A qubit in a Josephson junction can be in both states simultaneously. Not. Either 0 or 1, but we do not know which yet. Not. Switching back and forth too fast to see. Both. At the same time. This is quantum superposition, and it is not a metaphor. It is a measurable physical state described by what physicists call a probability amplitude, a complex number that encodes both the likelihood of each outcome and a phase relationship that determines how different superpositions interfere with one another. This interference, this ability for probability amplitudes to add constructively or cancel destructively the way waves do, is the entire basis of quantum computation. The machine is not guessing faster. The machine is navigating a space of possibilities using wave-like interference in a way that has no classical equivalent. But all of this only works if the system stays coherent, if the delicate superpositions and phase relationships are maintained long enough for the computation to complete. And this is where the engineering challenge becomes almost absurd in its difficulty. You are building the most powerful information processing device in human history, a machine capable of performing computations that would take classical systems longer than the age of the universe, and you are building it inside an environment specifically designed to prevent any information from the outside world from reaching it. The machine can only compute in total isolation. The moment the outside universe interacts with it, the moment it is observed, measured, or disturbed in any way, the quantum states collapse. The computation ends. The answer is lost. Think about the paradox embedded in that. You're asking a machine to compute properties of physical reality, to simulate molecules, to model materials, to solve equations that describe the behavior of the universe, and to do that, you must hide the machine from the universe. You must cut it off from the very reality it is supposed to be describing. The computation happens in isolation, but the computation is about connection. It exploits quantum entanglement, a phenomenon where particles remain correlated across arbitrary distances in ways that no classical signal can explain. It uses superposition, the simultaneous existence of multiple states that classical physics says should be mutually exclusive. It operates according to rules that require, at a fundamental level, that the system not be part of a single, definite classical reality. The machine works. The outputs are real. The computation's complete. But the conditions required for it to work are conditions that seem designed to keep reality at bay. Why would a machine that computes reality need to be hidden from it? That question is not rhetorical. It is not philosophical decoration. It is a genuine engineering constraint that points at something deeper and stranger about what quantum computation is actually doing. The isolation is not incidental. It is load-bearing. The machine cannot work any other way. And as we are about to see, the reason it cannot work any other way has everything to do with the fact that the computation it performs does not fit inside the reality we can observe. Let us do some mathematics together. Nothing complicated, just counting. But we need to count carefully, because the place this counting leads is where the entire mystery lives. Start with a coin. One coin, you flip it. It lands heads or tails. 2 possible outcomes. Write that down. 2. Now take 2 coins, flip them both. How many possible outcomes are there? Heads, 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 tails, tails, heads, tails, tails. 4 possibilities. That is 2 times 2, which we write as 2 to the power of 2, or 2 squared, equals 4. 3 coins, 8 possible outcomes, 2 cubed equals 8. 4 coins, 16. 2 to the power of 4 equals 16. 5 coins, 32. 2 to the power of 5 equals 32. You see the pattern. Every time you add 1 more coin, the number of possible outcomes doubles. This is exponential growth. An exponential growth, even though we use the phrase casually, is something human brains are not built to grasp intuitively. We think linearly. We think in steps. Exponential growth does not move in steps. It moves in leaps that accelerate faster than intuition can follow. Let us keep going. 10 coins, 2 to the power of 10. That is 1,024 possible outcomes. 1,024 different patterns of heads and tails across 10 coins. Still manageable. You could, if you had the patience, write them all down on a few sheets of paper. 20 coins, 2 to the power of 20. That is 1,048,576, just over a million. You're not writing that down by hand, but a computer could list them all in a fraction of a second. 30 coins, 2 to the power of 30. That is 1,073,741,824. Just over a billion. Still within the range of things a computer handles routinely. Large, but not strange. 50 coins, 2 to the power of 50. That is 112 quintillion 589 quadrillion, 906 trillion 842 billion 624. More than a quadrillion. The number is getting unwieldy to say out loud, but it is still just a number, still computable. Now here is where it starts to become something else. 100 coins, 2 to the power of 100. That number is approximately 1 nonillion, 228 quadrillion, 229 trillion, 401 billion, 496,703,205,376, more than a nonillion, a 1 followed by 30 zeros. Try to hold that in your mind for a moment, not as a symbolic string of digits, but as an actual quantity. 1 nonillion different possible patterns. If you tried to count them out loud, 1 per second, without sleeping, without stopping, you would still be counting trillions of years from now, long after the sun has burned out, long after the stars themselves have gone cold, and we're not even close to where this is going. 200 coins, 2 to the power of 200. That is approximately 1.6 times 10 to the power of 60. A 1 followed by 60 zeros. There is no common name for this number. We have left the realm where language has names for quantities. The number of grains of sand on every beach on Earth is somewhere around 10 to the power of 23. The number we are talking about is 10,000 trillion times larger than that. 300 coins, 2 to the power of 300. This is approximately 2 times 10 to the power of 90. A 2 followed by 90 zeros. Stop here. Do not move past this number yet. Sit with it. The total number of atoms in the observable universe, every atom in every star, every planet, every grain of dust, every molecule of gas in the vast spaces between galaxies, everything we can see with our most powerful telescopes in every direction, out to the edge of the observable cosmos, is estimated at around 10 to the 80 power, 10 to the 80th power. The number of possible states of 300 coins is 10 billion times larger than that. 10 billion times larger than the total number of atoms in the entire observable universe. Now let us be very clear about what we're saying, because this is the point where the abstraction has to become concrete. A classical computer made of atoms, made of transistors and circuits and memory chips, all built from matter, dares all existing in physical space, can only represent one state at a time. If you have 300 classical bits, your computer is in one specific pattern of zeros and ones. It can change to a different pattern. It can process through many patterns sequentially, but at any given moment it exists in exactly one state out of the 2 to the power of 300 possible states. A quantum computer with 300 qubits does something categorically different. A quantum computer with 300 qubits in superposition does not represent one state out of 2 to the power of 300 possible states. It represents all 2 to the power of 300 states simultaneously. Not sequentially, not approximately, simultaneously. All of them at once. The system exists in a superposition of every possible configuration of 300 quantum bits, and it operates on all of those configurations in parallel. This is not an interpretation. This is what the mathematics of quantum mechanics requires. This is what the outputs of quantum computers demonstrate. The interference patterns that produce the final answer can only arise if the computation was genuinely operating across the entire exponentially large state space simultaneously. The machine is not moving through those states one at a time, it is inhabiting all of them. And here is where the arithmetic stops being abstract and starts being a crisis. If the system is simultaneously in 2 to the power of 300 states, and each state requires information to describe it, requires physical representation somewhere, somehow, then where is that information? You cannot store 2 times 10 to the power of 90 states in 10 to the power of 80 atoms. The numbers do not work. You cannot fit something 10 billion times larger than the universe inside the universe. This is not an engineering limitation. This is not a question of building a bigger hard drive or waiting for better technology. This is arithmetic. The information required to fully describe the quantum state of a 300-qubit system exceeds the information storage capacity of all the matter in the observable cosmos. And 300 qubits is not a theoretical limit. It is a modest number. Google's Willow chip has 105 qubits. IBM's roadmap projects systems with thousands of qubits within the next several years. Researchers are talking seriously about million-qubit systems within 2 decades. Every additional qubit doubles the state space. A 400-qubit system would have a state space 2 to the power of 100 times larger than 300 qubits. The gap between what these systems require and what physical reality can contain does not shrink as the technology matures. It grows. Now, you might object. You might say, the system is not actually storing all those states the way a classical memory stores data. The probability amplitudes are not physical objects sitting in physical locations. The mathematics describes the system, but the description is not the same as the thing being described. That objection is reasonable. It is also not enough. Because the computation demonstrably takes place, the interference between all those states demonstrably occurs. The correct answer emerges from a process that, if it were classical, you would require examining an astronomically large number of possibilities in parallel. You cannot get the outputs these machines produce from a process that was only ever in one state at a time. The mathematics of how the answer is generated requires that the intermediate steps involve something operating across the entire superposition simultaneously. The question is not whether the system is in all those states. The mathematics of quantum mechanics requires that it is. The question is, what physical substrate is hosting that information? Where is it? Not in the chip. The chip is made of a few hundred atoms arranged in superconducting circuits. Even if you could use every atom in the chip to store one bit of classical information, you would run out of atoms long before you ran out of states. Not in the laboratory, not in the building, not in the city, not in the planet, not in the solar system, not in the galaxy, not in the observable universe. The arithmetic does not fit. So we are left with a choice, a very simple choice. Either the computation is happening somewhere else, somewhere outside the bounds of the single universe we can observe, or our arithmetic is wrong. The mathematics we use to describe quantum systems, the mathematics that has been tested and confirmed in literally millions of experiments over the last century, the mathematics that predicts the behavior of atoms and molecules and semiconductors with absurd precision, is fundamentally mistaken in a way that just happens to give correct answers every single time we check. That is the choice. Our arithmetic is wrong, or the computation is happening somewhere else, and our arithmetic is not wrong. The numbers are correct. The state space is real. The interference is real. The outputs are real. The machines work. So if the computation cannot be contained within this universe, where is it? That question, asked honestly, followed to its logical conclusion, leads to a place that most physicists in the 20th century were not willing to go. But one physicist went there anyway. in 1985, long before the hardware existed, and what he found was not a comfortable answer, it was a correct one. Oxford, England, 1984, winter. A physicist named David Deutsch sat alone in his office with a legal pad, working through a problem that no one had asked him to solve. He was not trying to build a quantum computer. No one was, not seriously, not yet. He was trying to understand what one would be, not what it would calculate, not how you would program it, what it would be doing physically when it ran. He had the mathematics. Everyone working in quantum mechanics had the mathematics. Schrödinger's equation, superposition, entanglement. The formalism worked perfectly. It predicted the outcomes of experiments with extraordinary precision, but the formalism did not tell you what was actually happening in physical reality when a quantum system evolved. It told you how to calculate probabilities. It did not tell you where the calculation lived. Deutsch was trying to follow the numbers to their physical conclusion. He started with the same arithmetic we just walked through. A quantum computer with n qubits inhabits a state space of 2 to the power of n dimensions. For large n, that state space is larger than anything that can be stored in the observable universe. This was not controversial. This was just mathematics. What was controversial, what Deutsch realized would be controversial, was the question that followed. If the computation is real, and the state space is real, then what physical system is hosting it? Not the chip, not the laboratory, not anything you can point to in this universe. So where? Deutsch wrote later that he found the conclusion uncomfortable. He was not looking for it. He was not trying to prove a philosophical point. He was just doing the accounting honestly, and the accounting left him with nowhere else to go. The computation, by necessity, had to be distributed across parallel instances of reality, not as a metaphor, not as a convenient way of speaking, as a literal physical description of where the work was being done. Each branch of the quantum wave function was performing a small piece of the calculation. The interference between branches produced the answer. You measured the result in your branch, but the labour had been done everywhere. This was the many worlds interpretation, not as philosophy, as physics, as the only framework in which the arithmetic of quantum computation made sense. But Deutsch did not invent many worlds. He inherited it. From a man who had died 2 years earlier, largely forgotten, whose idea had been dismissed, gutted and buried by the most powerful figure in 20th century physics. His name was Hugh Everett III. Princeton, New Jersey, 1957. Hugh Everett was 27 years old, a doctoral student working under the supervision of John Wheeler, one of the most respected physicists in the world. Everett was brilliant. Everyone agreed on that. He had a mind that moved in directions other people did not see. And he had become obsessed with a problem that most physicists had learned not to ask about: the measurement problem. In quantum mechanics, our systems evolve according to Schrödinger's equation, smoothly, deterministically. A particle in superposition stays in superposition, evolving continuously according to precise mathematical rules until you measure it. At the moment of measurement, the superposition collapses. One outcome is selected, the others vanish, gone, as if they never existed. This collapse was not described by Schrödinger's equation. It was a separate postulate, added to the theory not because the math required it, but because observation required it. Every time you measured a quantum system, you saw one result. So the collapse had to happen, somewhere, somehow. But the equation said no such thing. The equation said the superposition continued, forever, branching, spreading, never collapsing. Everett's solution was radical in its simplicity. He said, what if the equation is right? What if there is no collapse? What if every possible outcome of every quantum measurement actually happens? not in sequence, not probabilistically in the sense that one wins and the others lose, but all of them simultaneously in parallel branches of reality. The observer does not collapse the wave function. The observer becomes part of it. The universe branches. One version of you sees outcome A, another version sees outcome B. Both are real, both continue. Neither is aware of the other because the branches no longer interact. This was Everett's doctoral thesis. He called it the relative state formulation. Later, it would be called the many worlds interpretation. He sent it to Niels Bohr, and Bohr was the towering figure of quantum mechanics, the architect of the Copenhagen interpretation, the view that quantum mechanics is a tool for predicting measurements, not a description of reality, and that asking what happens between measurements is meaningless. Bohr's intellectual authority over the field was absolute. To disagree with Bohr was to mark yourself as someone who did not understand the physics. Bohr dismissed Everett's idea, not with a detailed refutation, with silence, with the kind of institutional coldness that ends careers. Wheeler, caught between his brilliant student and the most powerful man in his field, told Everett to revise, to soften the claims, to make it more palatable. Everett rewrote the thesis, cut it down, published a shortened, decautious version in 1957 that attracted almost no attention. And then he left physics. He took a job at the Pentagon working on nuclear wargame theory and operations research during the Cold War. He was good at it. He made money. But by all accounts, he was not happy. Colleagues described him as distant. He drank heavily. His marriage suffered. His health declined. In 1982, at the age of 51, Hugh Everett III died of a heart attack in his home in Virginia. He never knew that his idea would be rehabilitated. He never saw the generation of physicists who would take many worlds seriously, not as speculation, but as arguably the most straightforward interpretation of quantum mechanics, the one that simply takes the math at face value without adding extra postulates. He never knew that a physicist at Oxford would, 3 years after his death, use his framework to make a prediction about machines that didn't yet exist. Machines that would, 40 years later, behave exactly as that prediction required. Deutsch needed Everett, not because many worlds was philosophically satisfying, because it was the only framework that made quantum computation physically coherent. If quantum computers work, and they do, then the many worlds interpretation is not just one option among many. It is the description of reality that the hardware requires. Deutsch published his argument in 1985 in the Proceedings of the Royal Society. The paper was titled Quantum Theory, the Church-Turing Principle, and the Universal Quantum Computer. It is one of the most important papers in the history of computer science, and for a very long time it was also one of the most ignored, not because it was wrong, because it was too right in a direction most people were not ready to go. The claim was clean. A quantum computer cannot operate within a single universe. The exponential resources it accesses are not available in any single branch of reality. The computation is distributed across parallel worlds. The interference between those worlds produces the answer. This is not philosophy. This is the only physical picture that survives honest accounting. Deutsch made that argument in 1985, before quantum error correction was proven possible, before Bell's inequalities were tested without loopholes, before satellites demonstrated entanglement over continental distances, before Google or IBM or anyone else had built hardware that could run a quantum algorithm. He was right, and the machines we have built in 2024 fit his prediction better than any alternative framework. Hugh Everett died believing his idea had been dismissed as nonsense. David Deutsch spent decades being politely ignored by colleagues who thought many worlds was untestable metaphysics. And then we built the hardware, and it worked, and the question of where the computation happens became unavoidable. Princeton, New Jersey, the 1950s. Albert Einstein was in his 70s. He had spent the previous 4 decades reshaping humanity's understanding of reality. He had shown that space and time were not fixed backdrops, but flexible structures that bent under the weight of matter and energy. He had predicted that massive objects would warp space-time so severely that not even light could escape. Black holes, though he never called them that. He had predicted that accelerating masses would send ripples through the fabric of space itself, gravitational waves that would be detected 60 years later, exactly as he described. He was, by any measure, the greatest physicist of the 20th century, perhaps the greatest who ever lived. And he thought quantum mechanics was wrong. He had not wrong in its predictions. He knew the math worked. The equations predicted the outcomes of experiments with absurd precision, but wrong in what it implied about the nature of reality, wrong in its refusal to answer the question of what was actually happening between measurements. Einstein believed there had to be something deeper, something underneath the quantum formalism, hidden variables he called them, information carried by particles that determined in advance what the outcome of any measurement would be. The randomness was not fundamental, it was ignorance. We simply did not have access to the hidden layer where the real physics was happening. This was not stubbornness, it was hope. A reasonable, carefully considered hope that the universe, at its deepest level, it was still the kind of place that made sense, local, deterministic, real in a way that did not require observers or measurements to bring it into being. In 1935, Einstein co-authored a paper with Boris Podolsky and Nathan Rosen, what became known as the EPR paper, arguing that quantum mechanics, as formulated, was incomplete. If 2 particles were entangled, measuring one appeared to instantaneously affect the state of the other, no matter how far apart they were. Einstein called this spooky action at a distance and found it unacceptable. The particles, he argued, must carry hidden information that determined their behaviour locally. No spookiness required. Just physics we had not yet uncovered. It was a good argument, a compelling one, and for 30 years, it sat in the literature as an unresolved philosophical dispute. Most physicists ignored it. Quantum mechanics worked, that was enough. Then, in 1964, a physicist named John Stuart Bell, working at CERN, did something unexpected. He turned Einstein's hope into a testable prediction. Bell showed that if hidden variables exist, if particles carry local information that determines measurement outcomes in advance, then the correlations between measurements on entangled particles must obey certain mathematical limits. He derived inequalities, specific numerical bounds that any local hidden variable theory had to satisfy. And then he showed that quantum mechanics predicts those bounds will be violated. This was no longer philosophy, this was physics. The 2 frameworks, local hidden variables and quantum mechanics, made different, mutually exclusive predictions about what you would observe in a carefully designed experiment. Nature would have to choose. The first serious test came in 1972. John Clauser, working with Stuart Friedman at Berkeley, built an experiment using entangled photons. They measured correlations. They compared the results to Bell's inequalities. The inequalities were violated. Quantum mechanics was right. Hidden variables, at least the local kind, were in trouble. But there were loopholes, technical issues with detector efficiency, timing gaps that, in principle, could allow a signal travelling at light speed to pass between detectors before both measurements were complete. If you were committed to saving local realism, you could argue the experiment had not fully closed the case. A decade later, in the early 1980s, Alain Aspect, working in Paris, designed a new series of experiments specifically to close the most important of those loopholes. He used faster switching, better detectors, longer distances. The results, published in 1981 and 1982, were even clearer. Bell's inequalities were violated with high statistical significance. The correlations were stronger than any local hidden variable theory could produce. Einstein's hope was fading, but the loopholes were not fully closed. Not yet. It took until 2015. A team led by Ronald Hansen at Delft University in the Netherlands ran what is now called a loophole-free Bell test. They used entangled electrons separated by more than a kilometre. The measurements were made fast enough that no signal travelling at the speed of light could pass between the detectors before both measurements were complete. The detection efficiency was high enough that the statistical loopholes were closed. The result? Bell's inequalities violated. Decisively, unambiguously. Local hidden variable theories were ruled out, not as a matter of interpretation, as a matter of experimental fact. The particles do not carry pre-existing information. There is no deeper classical layer underneath quantum mechanics determining outcomes in advance. The correlations between entangled particles are real, non-local, and cannot be explained by any mechanism involving information travelling locally through space. Einstein was wrong, not about relativity. Not about space-time or black holes or gravitational waves. About this. About the thing that troubled him more than anything else in his career. The universe does not work the way he hoped it did. In October 2022, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to 3 experimentalists: Alain Aspect, John Clauser, and Anton Zeilinger. The citation read, "For experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science." This was not a celebration. This was a verdict. The Nobel Committee does not award prizes for disproving beloved ideas. But that is what this prize marked: the end of a 50-year experimental campaign, the closing of every exit, the confirmation, beyond reasonable doubt, that the classical picture of reality, the one where particles have definite properties independent of observation, where causes precede effects locally, where the universe is made of things that exist in specific states, whether or not anyone is looking, is not correct. Local realism is dead, experimentally, definitively. And here is why that matters for everything we have been discussing. If there are no hidden variables, if there is no classical layer underneath quantum mechanics, then the question of where quantum computation happens becomes even harder to dismiss. The exponential state space is real. The superposition is real. The entanglement is real. These are not approximations or conveniences. They are physical facts about how the universe operates at its most fundamental level. When a quantum computer runs, it is not secretly doing something classical underneath. It is doing something genuinely quantum. Something that requires resources no single classical universe can contain. Something that operates according to rules that Einstein spent the last 30 years of his life hoping were not true. The experiments proved he was wrong. The hardware proved Deutsch was right. And the question we are left with is not whether quantum mechanics is strange. The question is, if there is no classical reality underneath it, then what is underneath? What is the substrate? What is the foundation? What is doing the work when a quantum computer computes, and the answer cannot fit inside the atoms of this universe? The door to Einstein's exit is closed, and the place that leaves us is more uncertain, more non-local, more fundamentally strange than even the architects of quantum mechanics were willing to fully accept. The universe is not what we thought, and the machines we are building are proving it. You have heard about entanglement. Almost certainly. It appears in science documentaries, in popular physics books, in articles about quantum computing that get shared online. And if you have absorbed the standard explanation, you probably understand it something like this. 2 particles become entangled, and after that, whatever happens to one instantly affects the other, no matter how far apart they are. Measure one particle and find it spinning clockwise, and you instantly know the other is spinning counterclockwise. Even if it is on the other side of the galaxy, that description is not wrong. But it is incomplete in a way that matters enormously, and the part that is missing is not a technical detail. It is the entire point. The standard explanation treats entanglement as a connection between two separate things. Two particles, each with its own independent existence, linked by some mysterious channel that allows information about one to instantly influence the other. The mystery in this picture is the channel. How does the influence travel? How fast? Through what medium? But this framing contains an assumption that quantum mechanics itself explicitly rejects. The assumption is that the two particles have independent existence at all. They do not. Two entangled particles do not have separate quantum states that happen to be correlated. They share a single quantum state. One state. Indivisible. A state that cannot be written as a combination of the state of particle A and the state of particle B, because particle A and particle B do not have individual states. There is only the state of the system, the whole thing, together as one object. Physicists have a technical term for this. They say the two-particle state is non-separable. It cannot be factored into independent pieces. If you try to write it as particle A is in state X and particle B is in state Y, you will find that no choice of X and Y gives you the right answer. The mathematics simply does not permit it. The two particles are not two things that are connected. They are one thing that appears from the outside to involve two locations. Let me try to make this concrete through analogy. And then let me show you where the analogy breaks. Imagine a pair of gloves. You separate them, put one in a box, ship it to the other side of the world. When you open your box and find a left glove, you instantly know the one in the other box is a right glove. No mystery. The information was there all along, encoded in the physical properties of the gloves at the moment you separated them. This is the hidden variable picture. This is what Einstein hoped entanglement actually was. Pre-existing, local, classical information. But we know from the Bell experiments that this is not what entanglement is. The glove analogy fails. Because unlike gloves, entangled particles do not have predetermined properties at the moment of separation. The measurement outcome is not revealed. It is created at the moment of measurement, and the correlations between outcomes at two distant detectors are stronger than any pre-existing local property could produce. So try a different analogy. Imagine a single musical chord. One chord played on a piano. It contains multiple notes, say 3. You can hear the notes individually if you listen carefully, but the chord is not 3 separate sounds that happen to be playing simultaneously. It is one sound with internal structure. The 3 notes do not exist independently within the chord and then combine. They are aspects of a single acoustic event. Separate them, and you no longer have the chord. You have something categorically different. An entangled quantum system is something like this. The individual particles are not separate entities that are correlated. They are aspects of a single quantum state with internal structure. Separate them, measure them, and you collapse something that was one thing into 2 classical outcomes. But before measurement, there is only the one thing. This analogy also breaks, eventually, but it breaks in a more productive direction, because it points at what entanglement actually is, not a connection between 2 things, but the non-separability of one thing. Now extend this to a quantum computer. A quantum processor running a computation is not a collection of individual qubits, each doing its own small piece of work, with their results combined at the end. During the computation, the qubits are entangled, deeply, thoroughly across the entire system. The quantum state of the processor is not the state of qubit 1, plus the state of qubit 2, plus the state of qubit 3, all the way to qubit 105. It is the state of the whole system, one state, indivisible, a state that lives in a Hilbert space whose dimensionality is 2 to the power of 105, larger than the number of atoms in the observable universe. The processor is not a collection of components operating in parallel. It is a single quantum object of extraordinary complexity, evolving as a whole according to Schrödinger's equation, using interference across its entire exponential state space to navigate toward the correct answer. And this creates a problem for one of the most basic questions we can ask about a physical system. Where is it? Right, we ask this question naturally about physical objects. Where is the processor? In the laboratory, on the chip, at the bottom of the dilution refrigerator. We can point to it. But the question of where the quantum state of the processor is, where the information that defines the computation lives, does not have the same answer. Because the quantum state is not localized in the way physical objects are. Entanglement is non-local by definition. The state of the whole system cannot be decomposed into states of its parts, and the parts are separated in space, so the state of the system is not here. It is not there. It is not in the space between. It is a property of the whole that cannot be assigned a location within any of the parts. When we ask whether computation is happening, we are implicitly assuming that computation is the kind of thing that happens in a place, that it can be located, that if you zoomed in far enough you would find the place where the answer was being worked out. Entanglement tells us that assumption is wrong. The quantum state that constitutes the computation does not have a location. It is a single, non-separable, non-local object distributed across, or perhaps more accurately, not contained by, ordinary space. And if the computation has no location within a single universe, then Deutsch's question becomes not just philosophical, but geometrically precise. The quantum state of a large processor is one thing. It is not here. It is not there. It is not anywhere in this universe that you can point to. Then where is the one thing? The next section will show you that this question has been tested, not in a laboratory on a tabletop, across more than 1,000 kilometers of open sky. And the answer came back the same way every time. The one thing does not care about distance. It does not care about space at all. 2 cities, 1 sky, 1 moment. In the Qinghai province of northwestern China, a physicist stood at a ground station in the city of Dlinga, detector aimed upward at the pre-dawn sky. At the same moment, more than 1,200 kilometers to the southeast, another physicist stood at a second station in the city of Lijiang, detector aimed at the same point above the horizon. Between them, the width of France and Germany combined, mountain ranges, river systems, the curvature of the Earth itself, which meant that the 2 stations could not see each other, could not signal each other, could not reach each other by any means faster than several milliseconds even at the speed of light. Above them both, moving silently through a sun-synchronous orbit approximately 500 kilometers above the surface of the Earth, was a satellite the size of a small car. Its name was Mikyus, after the ancient Chinese philosopher Mozi, who performed some of the earliest recorded experiments in optics more than 2,000 years ago. The choice of name was deliberate. What Mikyus the satellite was about to do was an experiment in optics that Mozi could not have imagined, that almost no one could have imagined even 50 years ago. Inside the satellite, a crystal was generating pairs of photons, not ordinary photons, but entangled ones, produced together from a single quantum event, sharing a single quantum state that could not be decomposed into individual pieces. 1 photon from each pair was directed downward toward Dlinga. The other was directed downward toward Lijiang. The satellite was not sending a signal. It was not transmitting information. It was distributing half of a single quantum object to each of 2 locations, separated by more than 1,000 kilometers. At Dlinga, the detector registered a photon, a measurement was made, an outcome was recorded. At Lijiang, at the same moment, adjusted for the small but measurable travel time of light from the satellite to each station, the detector registered its photon. A measurement was made, an outcome was recorded. Then the teams compared results. The correlations violated Bell's inequalities by more than 11 standard deviations. Let that number breathe for a moment. In experimental physics, a result at 5 standard deviations is considered a discovery, a result that would, by chance, arise less than 1 in 3 million times if the null hypothesis were true. 11 standard deviations is not even in the same conversation. The probability of obtaining those correlations by chance, or through any local mechanism, is so small that it does not have a meaningful English expression. It is not 1 in a billion. It is not 1 in a trillion. It is a number so close to 0 that writing it out would require more zeros than this paragraph has characters. The entanglement survived. More than that, it was not diminished. More than 500 kilometers of open atmosphere, the curvature of the planet, the relativistic effects of orbital velocity, the thermal noise of the Earth's surface. None of it weakened the quantum connection between those two photons. The Misius experiment, published in 2017 by a team at the Chinese Academy of Sciences led by physicist Jianwei Pan, was not the first demonstration of entanglement over large distances. Bell tests had been done across cities, across fibre optic cables, across open air over distances of tens and then hundreds of kilometres. But Misius represented a qualitative leap. It was the first time entanglement had been demonstrated through open atmosphere over intercontinental scale distances, using a moving platform in low Earth orbit, under conditions that no previous laboratory experiment had approached. The following year, the same team used Misius to conduct a quantum key distribution test between Beijing and Vienna, more than 7,000 kilometers apart, using the satellite as an intermediary relay. The first intercontinental quantum-secured communication in history. Security guaranteed not by computational difficulty, but by the laws of physics themselves. And in 2022, an upgraded version of the experiment demonstrated entanglement, maintained through a moving satellite with enough fidelity to serve as the foundation for practical quantum networks spanning continents. Here is what all of this tells us, not about communication, but about the nature of the resource that quantum computers exploit. Entanglement does not care about distance. This is not a poetic statement. It is a precise physical fact, tested across 1,200 kilometers of atmosphere with results that have been reproduced and confirmed. The quantum state shared between those two photons was not degraded by separation. It was not weakened by the space between them. It was not mediated by any signal travelling through that space, because no such signal could have travelled fast enough. The correlations were instantaneous, non-local, and real. What this tells us about quantum computation is this: the resource, the entanglement, the superposition, the quantum correlations that quantum computers exploit to access their exponential state space, is not confined to the physical volume of the hardware. It is not bounded by the chip. It is not limited to the space inside the dilution refrigerator. Entanglement, as the Misius experiment demonstrated with unmistakable clarity, is a global property of a shared quantum state. Geography cannot dissolve it. Distance cannot weaken it. Space, as we ordinarily understand it, this doesn't constrain it. If the resource has no location, if the quantum correlations that power computation operate across distances that dwarf any hardware, then the question of what contains those correlations becomes urgent in a new way. They are not contained in this city, not on this continent. Misius showed they can be maintained across a planet. But the deeper question is not how far entanglement can stretch within space. The deeper question is whether space itself is the right container. Because there is a proposal, published in 2013 by two of the most respected theoretical physicists alive, suggesting that space is not where entanglement lives. Entanglement is where space comes from. And if that proposal is correct, then quantum computers are not running computations inside the universe. They may be running computations in the structure that generates it. Let me ask you something you've probably never been asked before. What is space? Not what is in space. Not the stars, the planets, the dust clouds, the galaxies stretching out in every direction. Those are the contents. I am asking about the container, about space itself, about the thing that exists between objects, the distance between your hand and this screen, the void between the Earth and the Moon, the vast emptiness between galaxies that light takes millions of years to cross. What is that? Most people, if they think about it at all, treat space as a background, a stage, a fixed, featureless arena in which events occur. Objects move through space, forces act across space, time passes within space, but space itself is just there, passive, permanent, some prior to everything that happens inside it. Einstein complicated this picture. He showed that space is not fixed and featureless. It bends, it stretches, it responds to the presence of matter and energy. The geometry of space is not a background. It is a dynamic physical field that participates in the events happening within it. Massive object curves space-time. That curvature is what we experience as gravity. This was revolutionary, but it still treated space as fundamental, as the thing from which geometry emerges. The question Einstein didn't answer, the question that has resisted every attempt at a clean answer for a century, is where space-time itself comes from. What generates it, what it is made of at the deepest level. In 2013, I and two theoretical physicists proposed an answer so radical that the community is still processing its implications. Juan Maldacena and Leonard Susskind, between them, two of the most cited physicists in the history of the field, published a paper whose title was a mathematical equation, ER equals EPR. ER stands for Einstein-Rosen. In 1935, Einstein and Nathan Rosen described a theoretical structure predicted by general relativity, a bridge connecting two distant regions of space-time, a wormhole, a topological shortcut through the geometry of space itself. EPR stands for Einstein, Podolsky and Rosen, the same 1935 paper about quantum entanglement that we discussed earlier, the one where Einstein argued that spooky action at a distance implied quantum mechanics was incomplete. Both papers were written in the same year, by some of the same people, and for 78 years they were treated as completely unrelated. Wormholes were a curiosity of general relativity. Entanglement was a feature of quantum mechanics. Two separate theories, two separate phenomena, no connection. Maldacena and Susskind proposed that they are the same thing. Every pair of entangled particles in this picture is connected by a microscopic wormhole. Not metaphorically, physically. The quantum entanglement between two particles is a geometric connection, a tiny, non-traversable bridge in the fabric of space-time linking the two particles, regardless of the space between them. The particles are not correlated across space. They are connected through a structure that bypasses space entirely. But the conjecture goes further than that, much further. If every entangled pair of particles is connected by a wormhole, and if the universe contains an astronomical number of entangled pairs, then the entire geometric structure of space-time, the distances, the directions, the curvature, the connectivity of the universe we inhabit, is a consequence of the entanglement structure of quantum states. Space is not the container in which entanglement exists. Entanglement is the source from which space emerges. More entanglement between two regions means more geometric connectivity between them. More wormhole-like bridges threading the space. Stronger, more connected geometry. Less entanglement means the geometry pulls apart. The regions become more distant, more disconnected. In the mathematical limit of zero entanglement, the the geometric connection disappears entirely. Space does not become thin or weak. Space does not exist. Space is made of quantum connections. It is woven from entanglement the way fabric is woven from threads. Remove the threads and there is no fabric. Remove the entanglement and there is no space. This is not a fringe idea. Maldaceno's work in the late 1990s, known as ADS/CFT correspondence, established the most precisely tested duality in theoretical physics, a concrete mathematical equivalence between a theory of quantum gravity and a quantum field theory on the boundary of that space-time. ER equals EPR extends this framework. It has not been proven from first principles. It has not been falsified. It is a conjecture, but a conjecture supported by deep mathematical consistency and taken seriously by the best theoretical physicists in the world. Now, apply this to quantum computers. A quantum processor running a computation is generating and manipulating a complex entanglement structure across its qubits. In the ER equals EPR picture, it is doing something else simultaneously. It is generating and manipulating geometry. The entanglement structure of the processor is, in a precise technical sense, a geometric structure, a network of microscopic connections threading through a space that underlies the space we can observe. The computation is not happening in space. It may be happening as space. As a geometric structure being constructed, navigated, and dissolved by the entanglement dynamics of the qubits. This means when a quantum processor accesses its exponential state space, when it simultaneously inhabits 2 to the power of 105 states and uses their interference to compute, it may be traversing a geometry that it is itself generating. A geometry that has no classical description. A geometry that exists at a layer of reality below the space-time we experience. The machine is not running inside the universe. The machine may be running inside the structure that builds the universe, and if space emerges from entanglement, then the question we've been building towards since Section 3 takes on a different character entirely. We asked, if the computation cannot fit inside this universe, where is it? The answer ER equals EPR offers is not somewhere else in space. The answer is that space is the wrong category. The computation lives in the entanglement structure from which space is made. It lives in something more fundamental than space, something prior to space, something that space is a consequence of. Which raises a question that is genuinely difficult to think about without feeling the ground shift beneath you. If space is made of entanglement, what was there before the entanglement? What is the ground floor? Here is a question almost no one has ever asked. What happens to information when you delete it? Not where does it go? Not can it be recovered? What happens to it? Physically, thermodynamically. What does the universe do when a bit of information is erased? Most people, if they think about it at all, assume the answer is nothing. Information is abstract. It is a description of physical things, not a physical thing itself. You delete a file, the magnetic domains on a hard drive flip to a neutral state, and nothing of consequence occurs except that the file is gone. The universe does not notice. The universe does not care. In 1961, a physicist named Rolf Landauer working at IBM proposed that this assumption was wrong. He argued from first principles of thermodynamics that erasing one bit of information must release a minimum amount of heat into the environment, not approximately, not as an engineering limitation, exactly. The minimum energy dissipated by erasing one bit is equal to the temperature of the system multiplied by Boltzmann's constant multiplied by the natural logarithm of 2. This is Landauer's principle, and it's not just a theoretical curiosity. It means that information erasure has a thermodynamic cost. That destroying information, truly, irreversibly erasing a bit, requires energy and releases heat. That information processing is not just described by physics, it is constrained by physics. It participates in the same thermodynamic accounting as every other physical process in the universe. For 50 years, a Landauer's principle was considered plausible but experimentally untested. The energy involved in erasing a single bit is extraordinarily small, on the order of 10 to the power of minus 21 joules at room temperature. Detecting it required experimental techniques that simply did not exist until the early 21st century. In 2012, a team led by physicist Sergio Ciliberto at the University of Lyon confirmed Landauer's principle directly. They used tiny colloidal particles trapped in a controlled laser potential, a system where individual bits of information could be encoded in the position of a single particle and erased in a controlled way. The heat released during erasure was measured. It matched Landauer's prediction to within experimental error. Information erasure generates heat. The result has been confirmed multiple times since in different experimental systems by different teams. It is no longer a theoretical prediction. It is an experimental fact. Information is physical. Not in the loose, metaphorical sense that we use information to describe physical things, in the strict thermodynamic sense that information has mass energy consequences, that the act of destroying information changes the physical state of the universe in a measurable way, that you cannot erase a bit without paying a physical price. John Archibald Wheeler spent the last decades of his life following this idea to its logical conclusion. Wheeler was not a marginal figure. He coined the term black hole. He worked alongside Niels Bohr on nuclear fission. He was Richard Feynman's doctoral supervisor. He was one of the central architects of 20th century physics, and in his 70s and 80s, he became increasingly convinced that the field had been asking the wrong foundational question. Physics had spent 3 centuries asking, what is the universe made of? The answers had progressed from atoms to molecules to particles to quantum fields. Each layer revealed something smaller, something more fundamental. But Wheeler believed this sequence of answers all shared a hidden assumption. They assumed the universe was made of stuff, of physical substance, of matter and energy that then, incidentally, carried information about its own state. Wheeler proposed inverting the assumption entirely. He called it from bit. The idea, every physical thing, every particle, every field, every region of space-time, every observable property of every system in the universe derives its existence from information, from binary distinctions, from yes or no answers to yes or no questions. The physical world does not generate information as a byproduct. The physical world is information, taking on the appearance of substance when it is observed, measured and recorded. The it of physical reality comes from the bit of binary choice. This is a staggering claim. It means that asking what is matter made of is asking the wrong question. Matter is not made of anything more fundamental than information. Matter is what information looks like when it becomes physical. The electron is not a tiny object that has properties we describe with numbers. The electron is the numbers. It is the set of answers to all possible questions you could ask about it. The universe is not a physical system that can be described by information. The universe is an informational system that appears physical. Landauer's principle connects to this at the thermodynamic level. Wheeler's it from bit reaches for it at the ontological level. And a third line of evidence converges on the same conclusion from the direction of gravity and geometry. It is called the holographic principle. In the 1990s, work by Jacob Bekenstein and Stephen Hawking on black hole thermodynamics established something unexpected. The maximum amount of information that can be contained within any region of space is not proportional to the volume of that region. It is proportional to the surface area of its boundary. Think about what this means. If you double the radius of a sphere, you increase its volume by a factor of 8. But the maximum information content of that sphere only increases by a factor of 4, proportional to the surface area, not the volume. No matter how much matter you pack into a region, there is a hard limit on how much information it can contain, and that limit is set by the boundary, not the interior. The information is not in the 3-dimensional volume, it is on the 2-dimensional surface. This is not a theoretical preference. For black holes, it is an exact result derived from quantum mechanics and general relativity simultaneously. Two theories that agree on almost nothing at their interface but agree on this. The information content of a region is bounded by its surface area, measured in units of the Planck length squared. The holographic principle generalizes this to the entire universe. The observable universe has a boundary, the surface from which light has had time to reach us since the Big Bang. The maximum information content of everything inside that boundary is proportional to the area of that surface. The 3-dimensional world we inhabit, every particle, every field, every quantum state, every thought and event and structure in the cosmos, may be a projection of information encoded on a 2-dimensional boundary we cannot directly see. We may be living inside a hologram, not in the science fiction sense, in the precise, mathematical, thermodynamically grounded sense that the physics community means when it uses that word. Now bring this back to quantum computers. If information is the ground floor of reality, if matter is what information looks like when it becomes physical, if space-time geometry is a projection of informational structure, if the thermodynamic cost of erasing a bit is the universe enforcing its own bookkeeping, then a quantum computer is something more specific than a calculating machine. A quantum computer is a physical system operating as close to the information layer as any technology we have ever built. It does not just process information about reality. It manipulates the quantum informational structure from which reality appears to be constructed. It operates in Hilbert space, the mathematical space in which quantum states live, which is, if Wheeler and Landauer and the holographic principle are pointing at the same truth, not just a convenient mathematical description, but the actual substrate. The computation is not running on top of reality. It may be running in the layer that reality runs on. And if that is true, if quantum computers are genuinely operating at the level where information becomes physical, then the practical consequences are not confined to laboratories. They reach into every encrypted communication, every financial transaction, every private exchange that depends on the assumption that certain mathematical problems are hard. Because at the information layer, the hardness of problems looks different than it does from the surface, and some problems that look hard from here look very different from there. Somewhere right now a server is running, not doing anything dramatic, not breaking codes or stealing secrets, just logging, recording, storing every packet of encrypted internet traffic it can reach, banking transactions moving between institutions, medical records transmitted between hospitals and insurers, diplomatic cables, intelligence communications, private messages between people who believe, reasonably, that the encryption protecting those messages is unbreakable. The server is not trying to decrypt any of it. It cannot. Not today. The mathematics protecting that data is, by current computational standards, effectively impenetrable. The encryption keys are large enough that factoring them on classical hardware would take longer than the age of the universe. The server knows this. The people running the server know this. They are not storing the data to read it now. They are storing it to read it later. This strategy has a name inside the national security and cryptography communities. It is called harvest now, decrypt later. And it is not a theoretical concern. It is not a scenario planners invented to justify budget requests. It is a documented, operationally active approach being pursued by state-level intelligence agencies right now, today, while you're reading this. The logic is straightforward and patient. The data being transmitted today is encrypted with algorithms whose security rests on a single mathematical assumption: that factoring the product of two very large prime numbers is computationally hard enough that no machine could do it in any useful time frame, hard enough to be, for practical purposes, impossible. That assumption is not permanent, it is conditional. It holds only as long as no sufficiently powerful quantum computer exists, and a sufficiently powerful quantum computer running an algorithm called Shor's algorithm, published in 1994 by mathematician Peter Shor, the same person who later proved quantum error correction was possible, would reduce that factoring problem from effectively impossible to tractable. Hours, perhaps, may be faster. RSA encryption, the mathematical structure protecting most public key cryptography, the foundation of secure internet communication, would not be weakened. It would be broken completely. The padlock would not become harder to pick. It would disappear. A communication encrypted today under RSA with a 2048-bit key is, against classical hardware, secure for centuries. Against a Shor-capable quantum processor, it is an open file. The harvest now, decrypt later strategy does not require breaking the encryption today. It requires only storing the ciphertext today and waiting. When the quantum hardware arrives, in 10 years, in 15, in 20, everything collected in the interim becomes readable. Every transaction, every message, every classified communication that passed over the internet during the harvest window. The clock on that data started running the moment it was transmitted. The fact that it is still encrypted today is not security, it is a delay. The people who understand this best are not being quiet about it. They are spending money, serious time, serious institutional attention. In 2016, the National Institute of Standards and Technology, NIST, the American federal agency responsible for setting technical standards that govern everything from manufacturing tolerances to cybersecurity protocols, launched a public competition. They were looking for new cryptographic algorithms, not improvements to existing ones, replacements, algorithms built on mathematical problems that quantum computers cannot efficiently solve. The competition ran for 8 years. It attracted submissions from cryptographers around the world. Hundreds of candidate algorithms were submitted, evaluated, attacked, broken, revised, and re-evaluated. In 2024, NIST published its final post-quantum cryptographic standards. The primary algorithms, Crystal's Kyber for key encapsulation, Crystal's dilithium and Falcon for digital signatures, are built on mathematical structures called lattices, where no quantum speed-up analogous to Shor's algorithm is currently known to exist. These standards are being deployed now, in government systems, in financial infrastructure, in the protocols that underlie the internet itself. The transition is underway. 8 years of work, billions of dollars in preparation, global coordination across dozens of governments and thousands of institutions. This is not a precautionary measure taken against a remote possibility. This is a response to a threat that the people with the deepest knowledge of the timeline believe is coming. Not might come, is coming. The only open question is when, and here is the signal worth reading carefully. NIST completed its competition in 2024. Deployment of new standards is being treated as urgent, not eventual, across NATO governments and allied intelligence agencies. The United States National Security Agency issued guidance in 2022 instructing all national security systems to begin transitioning to post-quantum cryptography immediately. The classified assessments driving these decisions are not public, but the decisions themselves are public, and decisions do not get made at this scale and this speed unless the internal estimates are alarming. Nobody knows exactly when a Shor-capable machine will exist. Current public estimates from credible sources suggest a decade or more away. but those estimates had been wrong before. The pace of Willow's error correction results was not predicted by the most optimistic public roadmaps from 2 years earlier. The history of this field is a history of surprises, and the surprises have not, on balance, been in the direction of slower progress. What we know is this: the encryption protecting your banking, your medical records, your private communications was designed for a world without quantum computers. That world is ending. The replacement infrastructure is being built right now, in parallel, as quickly as institutions can move. The server storing your encrypted data is still running, still logging, still patient. The mathematics it is waiting on is no longer a permanent barrier. It is a countdown, and encryption, it turns out, is not even the most unsettling place where quantum computing changes the rules, because quantum hardware is not developing in isolation. It is developing alongside another technology that was already, by itself, the most transformative development of the early 21st century, and when the two converge, the opacity that each creates individually becomes something qualitatively different, something that cuts deeper than broken encryption, something that reaches into the question of whether the most powerful tools we are building can be understood by the civilization that builds them at all. There is a problem that almost nobody is talking about loudly enough, not because it is classified, not because the people who understand it are hiding it, but because it sits at the intersection of two fields that have not yet fully reckoned with each other, and the intersection is where the strangest and most consequential things are starting to happen. The problem is opacity, and it compounds. Start with artificial intelligence. The large language models and neural networks that have transformed computing over the last several years are, in a precise technical sense, partially opaque to the people who build them. Not opaque in the sense that the code is hidden. The code is public. The architecture is documented, the training procedures are described in papers. But the internal representations, the way a large neural network encodes concepts, builds relationships, combines patterns to produce any particular output, live in a space of millions or billions of parameters whose interactions cannot be traced the way you would trace a classical algorithm. You can probe these systems from the outside. You can run interpretability experiments, look for circuits within the network that correspond to specific behaviors, identify features the system appears to be tracking. Researchers do this carefully and publish what they find, but you cannot read the reasoning. You cannot follow the logic step by step. You cannot look at a specific output and reconstruct with confidence the full chain of internal operations that produced it. This is a known limitation. It is widely discussed. It is the subject of an entire subfield called AI interpretability, which is growing rapidly precisely because the opacity is recognized as a genuine problem for safety, accountability, and scientific understanding. Now add quantum computing. A quantum processor running a computation operates in a Hilbert space, whose dimensionality exceeds the information capacity of the observable universe. The intermediate states of the computation, the superpositions, the entanglement patterns, the interference amplitudes that navigate the exponential state space toward the correct answer, cannot be observed without destroying the computation. This is not a limitation of current measurement technology. It is a fundamental feature of quantum mechanics. Observing a quantum state collapses it. The act of looking changes the thing being looked at. When the computation finishes and you read the output, you're seeing the result of a process that occurred in a space you cannot examine, following dynamics you cannot simulate, exploiting correlations that have no classical description. The intermediate steps are not merely hidden, they're inaccessible by definition. This is the second black box. Now put them together. Researchers are already using classical AI systems to design and optimize quantum circuits. Machine learning algorithms that identify patterns in noisy quantum outputs compensate for hardware-specific error signatures. discover circuit architectures that human engineers had not anticipated. The AI is already serving as an interface between quantum hardware and human-readable results. The next step, already underway in research laboratories, is to use quantum hardware to enhance AI itself, to run certain linear algebra operations that underlie neural network training and inference on quantum processors, to use quantum interference to navigate optimization landscapes that classical gradient descent cannot efficiently traverse, to build hybrid architectures where classical AI and quantum processors exchange information in tight loops, each enhancing the other's capabilities. When that integration matures, consider what happens to a single computation. A classical AI, whose internal reasoning cannot be fully traced, designs and optimizes a quantum circuit. That circuit runs on quantum hardware, whose internal operation cannot be simulated or observed. An output emerges, the output is used. No human anywhere in that chain can tell you step by step how the answer was produced. Not because anyone is being careless or secretive, because the two systems are each, individually, opaque in their own way, and the opacity does not add, it multiplies. The implications are concrete, not abstract. In drug discovery, a quantum AI system models molecular interactions at a level of precision that classical computers cannot approach. It identifies a candidate compound. The output enters the drug development pipeline. The reasoning that produced it cannot be reconstructed. If the compound works, we may never fully understand why. If it fails, or worse, if it causes harm that was not predicted, the causal chain that led to the recommendation may be permanently unrecoverable. In financial modeling, quantum AI systems identify correlations in market data that no classical algorithm finds. They produce trading strategies or risk assessments. Those strategies are deployed. The models that generated them cannot be audited in the traditional sense. When the market moves in unexpected ways, the question of whether the model anticipated that movement, failed to anticipate it, or actively caused it through its own trading behavior may have no clean answer. In climate simulation, quantum AI systems model atmospheric and oceanic dynamics at resolutions currently impossible. They produce projections. Those projections inform policy decisions affecting billions of people. The internal logic of the projection is not fully traceable. In each case, the system produces an output. The output is useful, perhaps extraordinarily so, and the process that generated it is opaque from two directions simultaneously. There is a version of this story where that is acceptable. We use black boxes constantly. Weather forecasts come from models whose internal dynamics no single person fully understands. Medical treatments work through mechanisms that are known approximately, not completely. The global financial system produces prices through processes that no regulator can fully simulate. Black boxes with useful outputs are part of how civilization functions. But there is a specific feature of scientific knowledge that black boxes undermine. Not just the ability to use results, the ability to understand them, to know not just that something works, but why it works, to build mechanistic models that predict behavior in genuinely novel circumstances, to catch errors before they propagate into systems that depend on the outputs being correct. And here is the deeper concern, the one that goes beyond engineering and accountability. Human intuition was built by evolution for a classical world. We track objects through space. We reason about causes preceding effects. We build mental models of systems we can observe with our senses and probe with our instruments. Our entire cognitive architecture is calibrated for a reality where things have locations, where properties are definite, where correlations have local causes. None of that equipment works in the space where large quantum systems operate. The patterns that quantum correlations create in high-dimensional Hilbert space, the structures that quantum interference can detect and exploit, are not just outside our intuitive reach. They are structurally inaccessible to minds built for classical navigation. This is not a matter of education or mathematical sophistication. It is a matter of what kind of patterns human cognition was shaped to find. When quantum AI systems begin operating effectively in that space, they may discover patterns in physical reality that are not just computationally opaque, but conceptually alien. Not because the systems are conscious or intentional, but because the patterns live in a space that human intuition simply cannot navigate, and the outputs those patterns generate will arrive in human-readable form without the human comprehensible reasoning that would allow us to evaluate them. We will have answers we cannot fully understand to questions we cannot fully formulate, and we will have to decide, as a civilization building these tools faster than we are building the frameworks to govern them, what we do with answers like that. What do you do with an answer you cannot verify from a process you cannot observe? That question does not yet have a satisfying answer. But the hardware that will make it urgent is being built right now, not by one company. Not in one country, by multiple teams in multiple nations pursuing multiple approaches to the same destination. And one of those approaches, if it works, would change not just the timeline but the entire character of the problem. Because it would not try to correct errors after they happen. It would make certain errors structurally impossible by hiding the information itself from the universe that is trying to corrupt it. Palermo, Sicily, March 1938. A man boarded a boat. His name was Ettore Majorana. He was 31 years old, a theoretical physicist widely considered a prodigy, even by the standards of a generation that included Enrico Fermi and Werner Heisenberg. Fermi, his mentor, had reportedly said that Majorana's genius was comparable to Galileo's and Newton's. He had just been appointed to a professorship at the University of Naples, a position secured despite his near-total refusal to publish, because the few papers he had released were so original that the university created a chair specifically for him. He boarded a night boat travelling from Palermo to Naples. He was seen by other passengers during the voyage. The boat arrived in Naples the following morning. Ettore Majorana was never seen again. No body was ever found. No confirmed sighting was ever made. His family searched, the police investigated, theories multiplied: suicide, voluntary disappearance, foul play, religious retreat, emigration under a false identity. None were confirmed. His fate remains to this day one of the enduring mysteries of 20th century science. A man whose mind operated at a level few could match simply vanished, as completely as a quantum state under observation. The year before he disappeared, Majorana had published a paper proposing a new kind of particle. Most particles in physics have antiparticles. An electron has a positron, a proton has an antiproton, opposite in charge but otherwise identical. When particle meets antiparticle, they annihilate. Majorana proposed that certain particles could be their own antiparticle. Neither particle nor antiparticle in the conventional sense, but something that is both simultaneously. Symmetric, self-conjugate, a particle equal to its own mirror image. The mathematics was elegant. The physical implications were profound, and for decades it remained unclear whether such particles existed in nature. They do. Not as fundamental particles, but as quasi-particles, collective excitations that emerge in certain condensed matter systems under very specific conditions. They are called Majorana zero modes, and they have a property that makes them uniquely suited to a challenge that has consumed the quantum computing field since its inception. They can protect quantum information by storing it in a place that does not exist. To understand topological protection, start with a simple analogy. Take a sphere, smooth, featureless, no holes. Now take a donut, one hole through the middle, no amount of stretching, bending or deforming, short of tearing the surface, can turn the sphere into the donut or the donut into the sphere. The number of holes is a topological property. It is global, not local. You cannot change it by poking one part of the surface, you have to rip the whole thing. Topological properties are structurally stable in a way that local properties are not. A scratch on the sphere's surface is a local defect. Erase it and the sphere is unchanged. But the number of holes is not a defect. It is the geometry itself. It cannot be erased without destroying the object entirely. Topological qubits encode quantum information in this kind of structure, not in the state of a single component, but in the global topological properties of a quantum system. The information is not stored at any particular location. It is stored in the relationship between spatially separated components, specifically in pairs of Majorana zero modes that must exist together and whose quantum state is defined by the correlation between them, not by either mode individually. This creates a form of protection that is qualitatively different from anything classical engineering has ever achieved. In every system you've encountered, adding components means adding potential failure points. A car has more ways to brake than a bicycle. A power grid has more failure modes than a generator. Complexity increases fragility. Topological qubits invert this. The information is stored non-locally. To corrupt it, you would need to simultaneously disturb both Majorana modes in a correlated way, a specific kind of error that random thermal noise essentially never produces. Local disturbances cannot access information that is not stored locally. The qubit is not shielded from the environment, it is hidden from the environment. The information lives in a global structure the environment is effectively blind to. Microsoft has spent more than 2 decades betting that this approach is not just theoretically elegant, but practically achievable. In February 2025, they announced a chip called Majorana 1, which they described as the first demonstration of topological qubits reliable enough to serve as a computing platform. The announcement was met with excitement and caution in equal measure. Microsoft has made claims in this area before that required later correction. A 2018 paper was retracted after errors in data analysis were identified. The community has reason to be careful. The 2025 announcement came with more detailed supporting evidence and passed initial peer review, but independent verification is ongoing. If it works, and the evidence is promising but not yet definitive, the implications reshape the timeline. A topological qubit requires far fewer physical components per logical qubit than superconducting error correction. Instead of thousands to one overhead, you might achieve 10 to 1 or better. A system with 1,000 topological qubits could deliver the computational power of tens of thousands of physical superconducting qubits. The path to practically useful quantum computation compresses dramatically. But step back from the engineering timeline for a moment, because the deeper implication here is not about speed or efficiency. It is about the nature of information itself. Topological qubits represent a different relationship between information and physics than anything we have built before. In every classical system, information has a location. This transistor is in this state. This magnetic domain is oriented this way. Information occupies a place in space. That assumption is so fundamental we barely notice we are making it. In a topological quantum system, information has no location. It is real. It can be read. It can be used for computation. But you cannot point to where it is. It lives in the global structure, in the relationship between parts, not in any part individually. And here is why that matters for everything we have been building toward. This is structurally identical to how quantum computation works in the many worlds framework. In both cases, the information is real, but non-local. In both cases, the protection comes from global structure rather than local features. In both cases, you interact with the output without being able to observe the substrate directly. You get the answer. You cannot watch it being computed. In Deutsch's framework, the computation is distributed across parallel branches of reality, and the interference between branches produces the result you measure in your branch. The information does not live in your branch alone. It lives in the global structure of the wave function. In topological quantum computing, the information does not live in any single Majorana mode. It lives in the correlation between modes in the global topological structure of the quantum system. The parallel is not just formal, it is telling us something about what quantum information is. Information that is real and operational but that has no location. Information that cannot be destroyed by local disturbances because it is not stored locally. Information that exists in a structure more fundamental than the space we can point to. Whether that structure is the branching wave function of many worlds or the topological geometry of a condensed matter system or both, different descriptions of the same underlying informational substrate, is a question the physics community has not yet settled. But the question is no longer abstract. The machines embodying these structures are being built, and they work. If information can exist without a location, if it can be real and verifiable and computable while not being anywhere you can point to, then the question of where reality stores itself becomes unavoidable. Not where in space, where in structure, what layer, what substrate, and whether we have accidentally built the first instruments in history capable of touching that layer directly. There is a question that has been circulating in popular science and philosophy for the last 2 decades, ever since a philosopher at Oxford named Nick Bostrom published a paper in 2003. The question is usually phrased something like this: could we be living in a computer simulation? Bostrom's argument was probabilistic. If civilizations can build simulations of conscious beings, and if they choose to run such simulations in large numbers, then simulated minds vastly outnumber real ones. Therefore, statistically, you are more likely to be simulated than real. The argument generated enormous attention. It made for compelling dinner conversation. But for most working scientists, it remained firmly in the category of unfalsifiable philosophy. Interesting to think about, impossible to test. Not something that changed how you did physics. Quantum computing changes that. Not because it brings us closer to building such simulations ourselves, though that question is worth asking separately, but because it fundamentally alters what we now know a simulation of our universe would require. And what it reveals is that simulating a universe like ours is not just computationally expensive, it may be impossible to do from anywhere simpler than the kind of universe being simulated. Let me show you why. Start with the Bell experiments. We covered these in section 5. The loophole-free test conducted in 2015 and honoured with the Nobel Prize in 2022 established, beyond reasonable experimental doubt, that there are no local hidden variables underneath quantum mechanics. The correlations between entangled particles are real, non-local, and cannot be reproduced by any classical computation involving information travelling locally through space. This has a direct implication for simulations. If you wanted to simulate our universe, to create a computational model that reproduces the quantum correlations we observe, you cannot take shortcuts. You cannot fake the entanglement with classical variables underneath. The Bell inequalities tell you that any such attempt produces correlations that are weaker than what we actually measure. The simulation would be detectably wrong. To simulate quantum entanglement, you must actually instantiate quantum entanglement. The simulation cannot be classical at its foundation and quantum only at the surface. It must be quantum all the way down. This is a hard constraint, not an engineering challenge. A physical one, established by experiment. Now go further, use the Deutsch framework. We established in section 3 that a quantum computation involving even a modest number of qubits, say 300, inhabits a state space larger than the total number of atoms in the observable universe. The computation cannot be hosted by any single classical instance of reality. Deutsch's argument, which we walk through in section 4, is that quantum computation requires the resources of parallel universes. The exponentially many branches of the wave function are doing the work. The interference between branches produces the answer. My if Deutsch is right, and the hardware behavior fits his framework better than any alternative, then quantum computation is not something that happens within a single universe. It is something that happens across many. Now apply this to the simulation question. If our universe is a simulation, and if our universe genuinely exhibits quantum behavior, superposition, entanglement, violations of Bell inequalities, then the simulator cannot be running a classical program. It must be running a quantum program. And if quantum programs require multiverse-level resources, then the simulator must itself have access to a multiverse. The thing running the simulation is not simpler than the thing being simulated. It is not a classical computer in a higher-order reality running a quantum approximation of our world. It is something embedded in a structure at least as quantum, at least as non-local, at least as exponentially complex as what we experience here. The hierarchy collapses. Bostrom's original argument assumed a clear separation. Base reality is real, the simulation is derivative, and the simulator stands outside, operating from a position of greater power and simplicity. That separation cannot be maintained if the simulation must be quantum, because a quantum simulation requires a quantum simulator. And a quantum simulator is not a fundamentally different kind of thing than the universe it simulates. It is, in every way that matters physically, the same kind of thing. The boundary between the real and the simulated stops being a boundary between fundamentally different categories of existence. It becomes, at most, a distinction of perspective, a question of which layer you are embedded in, not a question of which layer is ontologically prior. And here is where it becomes genuinely unsettling. We are building quantum computers, right now, in this universe. Whether this universe is base reality or a simulation or some third thing we do not have a word for yet, the machines we are building appear to operate by accessing resources that exceed the capacity of any single instance of reality. If we are in a simulation, then the quantum computers we are building inside that simulation are accessing the computational substrate of the simulation itself. They are drawing on the same multiverse-level resources that the simulator uses to run the simulation in the first place. We're not just inhabitants of the simulation observing its outputs. We're building devices that appear to touch the layer the simulation runs on. This was not intentional. No one set out to build a probe into the nature of reality. The goal was practical. Build a machine that factors numbers faster, that simulates molecules more accurately, that solves optimization problems classical computers cannot handle. But the machine that does those things, if Deutsch is right, if the Bell experiments mean what they appear to mean, if ER equals EPR and Wheeler's it from bit and the holographic principle are all pointing at the same truth, is also a machine that operates at a level of reality more fundamental than the one we experience directly. Sarah Chen, staring at the Willow error correction results for 45 seconds without speaking, was not just looking at an unexpected engineering success. She was looking at a device that should not be possible if reality is what we thought it was. A device that works by doing something that does not fit inside the universe we can see. The simulation argument, approach from this direction, stops being about probabilities and statistics. It becomes a physics question. What kind of substrate can host the quantum correlations we observe? What kind of structure can support the computation quantum computers perform? And the answer is not a classical computer in a higher reality. The answer is something at least as strange as a multiverse. If the simulation exists, the simulator is not outside the strangeness. The simulator is built from it, and we, whether simulated or not, whether base level or embedded, are now building machines that appear to access it directly. We did not set out to do this. We set out to build a faster computer, but the faster computer, it turns out, is also a window, not into a simulation necessarily, into the structure that underlies whatever this is, the informational substrate from which space and time and matter appear to emerge. If the simulation requires a quantum simulator, and quantum simulators require multiverse-level resources, then what exactly is outside? What is the container? What is the ground? The simulation argument does not answer that question. It just makes it impossible to ignore, because whether we are simulated or real, the machines work. And they work in a way that requires something larger, stranger, and more fundamentally non-classical than the three-dimensional universe we navigate with our bodies and measure with our instruments. The computation is happening. We just do not know where. And the question of where is starting to look like the most important question we have ever asked. Let us bring all the threads together now, not to tie them into a neat conclusion, they do not resolve that way, but to see what shape they make when you hold them all at once. The arithmetic that breaks the universe. A quantum computer with 300 qubits inhabits a state space larger than the total number of atoms in everything we can observe. The computation is real, the interference is real, the outputs are real. But the information being processed cannot fit inside the matter of this universe. The numbers do not work. The substrate required exceeds the substrate available. The man who saw it coming and was ignored, David Deutsch, working alone at Oxford in 1984, followed the arithmetic to its logical conclusion and arrived at a place most physicists were not willing to go. He said the computation must be distributed across parallel branches of reality, not as metaphor, as physics, as the only explanation that survives honest accounting. He published that claim in 1985, decades before the hardware existed. The hardware we built in 2024 behaves exactly as he predicted. The Nobel Prize that closed the exits, Alain Aspect, John Clauser, Anton Zeilinger, 50 years of experiments, each one closing another loophole, each one narrowing the space where classical explanations could hide. The final verdict, honoured in 2022, local hidden variables do not exist. There is no classical reality underneath quantum mechanics. The universe does not work the way Einstein hoped. The correlations are real, non-local, and unexplained by any mechanism that fits inside our ordinary picture of space and time. The satellite that proved entanglement ignores distance. Metius in orbit 500 kilometers above the Earth, distributing entangled photon pairs to ground stations 1,200 kilometers apart. The correlations held, more than 11 standard deviations beyond what any local mechanism could produce. Entanglement does not weaken with separation. It does not care about geography. It is a global property of a shared quantum state that space cannot dissolve. The geometry that may emerge from quantum connections, ER equals EPR, Maldacena and Susskind, 2013. The proposal that entangled particles are connected by microscopic wormholes, that the distances between things, the geometry of space-time itself, is not a fixed backdrop but an emergent property of quantum entanglement. More entanglement means more connectivity. Less entanglement means space pulls apart. In the limit of zero entanglement, there is no space. Space is not the container. Space is the content, the information layer that may be the ground floor of reality. Landauer's principle, confirmed experimentally in 2012, erasing information costs energy. Information is not a description of the physical. Information is physical. Wheeler's it from bit. The universe is not made of matter that carries information. The universe is made of information, and matter is what information looks like when it becomes physical. And the holographic principle, the maximum information in any region is proportional to its surface area, not its volume. The three-dimensional world may be a projection of two-dimensional data on a boundary we cannot see, the encryption that is already on a timer, harvest now, decrypt later. Servers are recording encrypted traffic right now, banking, medical, diplomatic, intelligence, not decrypting it, storing it, waiting. Because the mathematics protecting it is conditional on no one having a quantum computer powerful enough to run Shor's algorithm. Governments are spending billions replacing encryption standards, not as a precaution, but as a response to a threat they believe is coming. The timeline is not public. The preparation is the double black box of quantum AI. Classical AI systems whose internal reasoning cannot be fully traced, designing quantum circuits whose intermediate states cannot be observed. Opacity compounding, outputs emerging from processes that are opaque from two directions simultaneously. Drug discovery, financial modelling, climate simulation. In each case, answers we cannot verify from computations we cannot reconstruct, and eventually, perhaps, patterns discovered in quantum correlation space that human cognition, built by evolution for a classical world, simply cannot navigate. The topological qubit that stores information nowhere, Majorana zero modes, information encoded in the global structure of a quantum system rather than in any local component, real, verifiable, computable information that has no location, structurally identical to how quantum computation works in the many worlds framework, information that is real but non-local, protected by global structure rather than local features, producing outputs without observable intermediate steps. The simulation that would have to be quantum all the way down. Bell's inequalities rule out classical shortcuts. Any simulation of our universe must genuinely instantiate quantum correlations, not fake them with hidden variables, and if quantum computation requires multiverse-level resources, then any simulator running our universe must have access to multiverse-level resources. The simulator is not outside the strangeness. The simulator is embedded in it. The boundary between real and simulated dissolves. What do all of these threads point at? From different directions, using different tools, arriving at the same place? Reality at its most fundamental level is not classical. It is not local. It is not deterministic in the way 3 centuries of physics assumed. It is not contained within any single instance of any single universe. It operates according to rules that require resources no single branch of space-time can provide. And the machines we have built, accidentally, in pursuit of practical computation, are the first devices in human history that appear to operate at that level. We did not set out to probe the foundations of reality. We set out to build faster computers, to simulate molecules, to optimize logistics, to break encryption, practical goals, engineering goals. But the machine that accomplishes those goals is not a tool that works within the universe. It is a tool that works at a layer the universe appears to be built from, a layer where information has no location, where entanglement connects without space, where computation happens in structures larger than the observable cosmos. The machine works. That is not in dispute. It produces outputs. It completes calculations. The results are reproducible, verifiable, real. What we cannot do, what no one on Earth can do with confidence, is point at a mechanism and say, there. That is where the computation lives. That is the substrate being used. That is the part of reality doing the work. We are left with 3 options, only 3. The first is that quantum mechanics, as we currently understand it, is incomplete, that there is a deeper layer of physics we have not yet discovered that will explain all of the non-classical behaviour classically, that the exponential state space is a mathematical artifact, not a physical reality, that the entanglement will eventually be explained by local mechanisms we have not found. This is the option Einstein preferred. It is the option the Bell experiments have made extraordinarily difficult to defend. Every loophole has been closed, every exit has been tested. The data does not support it. It would require not just a new theory, but a new theory that reproduces all of quantum mechanics predictions while having a completely different underlying structure. No one has come close to building such a theory. The second option is that quantum mechanics is correct and complete, that the physical world genuinely operates the way the mathematics describes, that superposition is real, that entanglement is real, that the exponential state space is real, that Deutsch and Everett were right, the wave function branches, the branches are real. Quantum computation works because it is distributed across those branches. The interference between them produces the answer we measure. This is the option the evidence, taken at face value, most directly supports. It is also the most philosophically disorienting, because it requires accepting that most of reality, the vast majority of quantum branches, is permanently inaccessible to us. That we are one thread in an unimaginably vast tapestry, unable to see the whole, re-inferring its existence only through the interference patterns it creates. The third option is that there is something new, a framework we do not yet have, a physics that is neither classical nor quantum in the current sense, something that resolves the measurement problem, explains the entanglement, accounts for the computational resources, and tells us clearly what is happening when a quantum computer runs. This is the option most physicists would prefer. It is the move science has made before. When existing frameworks break, build a better one. But there is no candidate, no compelling proposal that most of the community agrees solves the problem. The measurement problem is more than 60 years old. The interpretations multiply. None commands consensus. The honest answer, the one that requires intellectual courage to say plainly, is this. We have built machines whose operation we cannot fully explain. We can operate them. We can program them. We can read their outputs. We can describe with precision how to build them, cool them, shield them, correct their errors. What we cannot do is describe the physical substrate in which their computation occurs. The three options remain. All of them require either revising our picture of reality in ways we have not yet achieved, or accepting that reality is stranger than any previous generation has had to confront. And there is something moving, something genuinely profound about standing here, at this moment, watching the machines work, measuring the outputs, confirming the predictions, and not knowing with certainty what any of it means. Every generation believes it is living at the edge of knowledge. Most are wrong. The mysteries they face turn out to have mundane explanations, but there are moments, rare, real, when humanity encounters something that genuinely does not fit, something that resists every attempt to reduce it to familiar terms. Quantum mechanics has been that thing since 1927. Quantum computing has made it impossible to defer the question. The machines are here. They are running. They are doing exactly what Deutsch said they would do. They are accessing resources that exceed the observable universe. They are exploiting correlations that have no classical explanation. They are demonstrating stability that should not exist. Yeah, you might find this frightening. There is a version of it that is frightening. The most powerful technology we have ever built, operating on principles we do not understand, using resources we cannot locate, in a substrate we cannot observe. But there is another way to hold it, as wonder, as the specific, particular quality of awe that belongs to standing at the genuine edge of human knowledge. Not the edge of what we have discovered, but the edge of what we can know with the tools we have. The place where the questions are clean and the answers are not. We have built something that works. We have built something that should not be possible if reality is what we thought. We have built it before we understood where its power comes from. And it works. The machine works. Oh, we just do not know where,